Okay, so yeah, welcome back, everyone. And so some adjustments from the last stream. Last night, or like the night before, an idea for this game I had came to me, which basically would turn this game from like a 2-hour game to at least a 10-hour game. And so if it's a 10-hour game, there's no way I can like record all of it on stream. It's just I'm gonna get fatigued. And so I just want to like curtail that and just make it a smaller project. And so I want to just first turn this into a demo in which a cube just rolls on the grid. And then once that's done, I then actually might just start making the game like off stream or something like this. I need to just figure out what it is first, and there's going to be so many literal moving parts to it. Okay, so first I just want to adjust the GitHub pages so that to reflect this new scope change. Yeah, so this demo is now a demo in which showing how a cube can roll across the grid. Or maybe like a simple demo in which a cube rolls on the grid, controlled by arrow keys. Do that, and then we'll update the where's like the settings, this one here. So let's just call it rolling cube demo. Rename. Okay. Great. Okay. This is a simple demo. Okay. Yeah, everything else should kind of be the same. So actually, for this like custom camera class, I don't think we're going to bother with this right now. Likewise, the grid drawing procedure we won't bother with, and likewise the matrix multiplication. We'll just get this thing rolling. I also realized that in terms of like the geometry of drawing the cubes, there's like way too much data here. This can massively be simplified. In particular, if we know like the geometry of one face of the cube, we can simply apply rotation matrices to get the other ones. And so I actually just want to begin by totally rewriting this render cube function to make it a lot simpler. So I think we first want to do is like write construct triangles at the top of the cube, and then rotate these around to get other faces. So if we're just doing triangles at the top of the cube, we just want 4 points. So in particular, we just want these. And then let's give these kind of different names, like maybe just 0, 0, 0, 1, like this. And then, okay, we're gonna have to think how to do the rotations in such a way that we can still correctly position this thing. Okay, so what's the next step? Because yeah, by the time we write these triangles here, we kind of want this position to be basically fixed. Like we want these ones to be the final ones. So Yeah, so currently we're rotating all of the points first, then shifting them. So I think this time around, if we have like the face at the very top, we want to like first rotate it to the correct side, and then do like a second round of rotations. Because this part's also messy as well. I kind of want to really remove a lot of that. Like a simple thing that could actually be fine is simply shifting the position of all of these triangles by adding this pos to like the first 3 arguments. Conceptually, that's actually kind of easier as well. And also too, if we construct this cube around the origin, then like shrinking the cube down to size is the same as shrinking the triangles. That is to say, so that would just be multiplying each of the position vectors in these triangles by the matrix as well. Okay, I think we can do this. So let's like first just create the only 2 triangles we actually need for the top. So we could say, so we can say like top, or maybe just like triangle 1, maybe triangle A, and we'll just make this. The P1 is 0, 0. It really annoys me in Zig that I can't simply fill this out in the usual way. 0, 1, 0, and then P3 is C11, and then we'll make the color. Let's actually change the coloring of the cube for a bit. Let's make these cubes have a constant color. And then likewise we want to define triangle B, where we simply change this one from 1, 0, 0, 1. And now we want to just rotate these triangles around to the other faces. Rotate the triangles in the top face around to the other positions. And so, well, how do we do this? Well, we're gonna end up with some. We can actually just have a fixed array of triangles. I reckon we should, like, this fixed array will have like 12 triangles, so we could just say a cube triangles is going to be an array of 12 triangles currently undefined. And then we just want to describe what each of these will be. So in particular, cube triangles 0 can just be the very first one. Triangle B can be the second one. And now we need to start rotating these things. So I kind of actually want to. It would be easy to rotate these if we can multiply a triangle by a rotation matrix. So let's write a function to do that. So let's do function mat multiply triangle. So this is given some matrix, and we'll it really should be an F32, and then a triangle. We do have a triangle type, right? Why did that not autofill? Let's move this to the top. XRS1. We'll put it like put it here. Okay. Not mul try. And then we're just gonna get back a triangle. And then now we want to do, we just want to define these new points, and the new points will be fairly simple. So we can say constant p1 is going to equal the mat multiply vec3. Is that the name of it? Mat vec multiply. Oh. Okay, this naming convention makes sense. Mat vec mul. In which case this should really be mat trimul, where we just multiply the first point of the triangle by this, and then likewise we do the same with the 1 and the 3, and then we basically just return the triangle that is p1 zig dot p3, and then try dot color. Okay. So this was mat try mul. So mat mul try. So I think now we want to do cube triangles 2 is equal to mat trimul. Okay, now we need to actually choose the matrix. So what were the ones we had before? Were they like x rot and was it rot x 90? Okay. And these things are just I8, so we need to convert them, but that is okay. So we can say like rot x 90 once we convert it with triangle A. And then likewise we can do something similar with triangle B. Okay, so let's think. So yeah, x was the since x is red, y is green, and blue is z, the top face is the one in which Z is 1. And so it's going to kind of be on that side. And so when we rotate by X around, we should cover like we basically should make like a cylinder that's like wrapping around the X-axis. And so similarly, we want to do like the rot 80, rot 270. But let's just make this better. So we can say const rot x 90 f32 is equal to the conversion function we had. What is it? If I do like mat33i8, this one here, okay, so mat33i8 to 33f32, rot x90, and then we'll just repeat this, but now with 180 and 270. Okay. Here we just want to do the F32 version. This 180. 180. We want this to still be 90. And we want this to be 3. Okay, and then we want to make this one 4, 5, 6, 7, and then what's that? No, insert 180, 180, 270, 270. Okay. Well, we'll just. It's fine. We can draw all of these at once. Actually, if we draw all of these at once, it might be kind of hard to see which is which. Okay, let's give some of these some colors. Okay, like since we're rotating around the X, the very top one should be the second one. So let's make this one like blue. So we can say like cube, triangles. Actually, we'll add a border later to like make these better. But let's just make this like, what are the colors we have? We do have blue. And then we'll make this one blue as well. And I think that should be, we'll make one of them green as well. Okay. But we now need to define the cube faces that are this way and that way. And so that is to say we'll need to do some more. So we'll make this 8, 9, 10, 11. And then here we're going to have to, if we're starting out with that face and we want to get this face and that face, we're going to want to rotate on the y-axis. So now let's do const rotate by y by 90. And this is going to be this mat33i8 to rot x 90. And then we'll also want to multiply by 270 as well. So we can make this one the 90, and the other one the 270. Okay, and then that fills up that array. And then, okay, if we want the one that's kind of facing us to be green, let's see, that's going to be the 270. So we want to change the colors of these ones to be green. Oops, I forgot to. Okay. Okay, so now we have those. We now want to like scale them appropriately. So, and then move them into the position. And so, with this scaling, if we first of all shrink these via we first of all want to shrink them by the identity. So we could just say like const half, and this is just going to be matrix scalar multiplication 0.5 and the identity. The identity might be just defined in terms of the i8s though, so we need to convert that. Isn't that I'm sure there's some nicer way of casting it, but whatever. And then I guess it is actually fine if we just do that. Okay, we'll just do that. We'll keep it as planned. So now we want to rotate the triangles by rot, and then adjust their position. And then really offset. It's more descriptive. So now I can just say for the triangles in cube triangles, call it try, we just want to say rather these triangles with index I, change these triangles again to be what we end up with when we do matrix try multiplication of this rot 2 and the try. Okay, and then this will rotate them and shrink them correctly, and then we want to offset their positions, so we can just eliminate all of this now. What's happening here? We don't need this anymore. And then for the triangles here, we just want these to be the cube triangles. Yeah, and then we want to offset them. So then to offset them, we can simply, once you've rotated them, add the offset to each of them. So then we can say cube triangle. Actually, let's do the following. Let's just say new try is equal to this thing, and then we can say n try dot p1. Oh, surely we can add vectors like this. Surely this is fine. And then finally set this equal to the new triangle again. Okay. Unless I severely stuff something up, I think this should be fine. But now the colors of the triangles will disappear. But, I mean, the colors of these cubes will disappear. Actually, I kind of want all of these cubes to have. The colors of some of these will change because of this weird stuff here, but this is more just like debug actually. Most of these ones should still be the appropriate colors. There's going to be some compile errors, but we'll get through it. Z run. Okay, so what's this first one? Expected type found equals. That's because we're not doing Odin anymore. And then expected something after initializer. Okay. What? Oh, I see. Are you serious? What's going wrong here? There's a semicolon on both of these. Like, did I not save it? Oh, I didn't save it. Okay. Undeclared rot 180. Really? Did we not define that last time? I guess we didn't. Interesting. So here we just need to do one less multiplication. And then likewise for the z's, but didn't we need the y's? I feel like I should just do these for all of them. Maybe it's a bit weird not having them individual ones. Okay, and then for the y, which is here, likewise we want to just replace all of the x's with y's. Okay. Yeah, this 32 doesn't make sense. It should be an F32. 277 render cube. Yeah, doesn't know what that is. Let's make this red to begin with. 369 cannot assign to constant. Yeah, because this is a variable. expected vector found matrix instead. Right. Okay. For the red cube, we want this to be red. We want the green cube to be green, and then we want the blue cube to be blue. Okay. Okay. So yeah, clearly this is correct. So we're done. Okay. Let's make the algebra correct. Get this actually looking right. Law. Okay. So let's check. Yeah, that is 0, 0. Hang on. So my claim was that I wanted these. I did all of these calculations thinking the face that we cared about was the one pointing. What is it? Z is this way. So, oh no. We want the Z to be. We want to be choosing this face instead. Okay. So if we're choosing this face, we want the Z to be 1 on all of these instead of this. Okay, so we want this to be 1, want that to be 1. Now we want this to be -1, -1, -1, +1, +1, and -1, 1. Okay. So let's see, that one, that one, that one, that one, yep. Then, since we're now doing this face, we can still rotate around the X, and that should be fine. And now now we actually want to rotate around the Y to get the other ones. So these ones, which we're still doing, so that should be fine. Let's give this a go. Okay, not perfect, but better. At least there is there's more cubes kind of appearing. So now this part here is concerning to me. In the same way, something isn't getting drawn at the front here. Okay, and let's actually update these colors. So, so let's make it so that for this first cube we have red, green, and blue. Then we want the very first face to be blue. So we'll make this 0 and 1. Then we want the top face to be green. So that is after rotating by 270 along the x-axis. That is, we want 6 and 7. This will also just check to see if I am understanding these directions correctly. Yeah, great. We've now set the colors the way we want to. Good. What's happening with this weird square here? What could be the problem? One way to fix this problem would be to start moving the camera. I feel like it would be fairly easy to move the camera. This is just also just to figure out what's actually going So let's do that. So the camera position is this, but this is like the initial camera position. Let's actually update this. Initial. Let's update this in the following way. Let's put this on a circle, and now we need to do timing stuff in Zig. Do I want to add in a looping camera? I want to just figure out the geometry problem. I feel like adding in the looping camera might take longer than just solving this. So we'll return to solving this, but if we get stuck, we'll add in the looping camera. That will help us figure out what's wrong. Okay, so it looks like like what's going on? Like, why is one of these offset in some weird way? Or even just like which one is offset in the weird way? Yeah, not sure what's happening. So this one's red, so presumably the thing that's drawing this is, well, it's not one of the ones we've changed. So it's either 2, 3, 4, 5 or 8, 9, 10. And it looks like something that is being incorrectly turned on the y-axis. But again, like, why would that actually... How would this stuff it up? We can narrow this down in a really crude way, but it will be effective. So let's say we just make like a black triangle that's equal to, basically this will be like a null triangle. So we can just say the origin P1 is it dot P1 is the origin, dot P2 is the origin, dot P3 is the origin, and then we'll make this color black, and then let's start making some of these triangles disappear. So in particular, we can say does it disappear when we get rid of these ones? It shouldn't. And likewise, we'll start with the ones that we know are not the problem. And 6, 7. Right. The dot color is equal to black. Come on, really. Unused. Oh, you got DJ. Okay. Okay, now we can kind of see at least what's going on. Oh, the rotation kind of helps as well. So yeah, it has been offset in some weird way. Like why? Okay, we'll continue making stuff disappear. But yeah, so if we make the other z-axis rotations disappear, I guess we have to do macros. There should be some way of disabling unused local constant in the compiler. Okay, and now we get the culprit. So what? Why? For rotating around by y. Is it the 270 that's the one that's wrong? Okay, so we found out which one it is now. So it is these ones. So yeah, the question is, why are these ones? What's wrong with these ones? Okay, so something wrong with rot y90. Okay, and then oh yeah, this is not meant to be a 0. This is meant to be, let's see, cosine. So what it is? What? So this is going to be cosine, sine. Sorry, cosine, negative sine, sine. This one here should be a 0. Maybe we'll align them like that. Okay. Better. Okay. Let's get back to here. Okay. Whatever. Okay. unused local constant, yeah, the BT is now a debug. Okay, now the cubes are being drawn correctly. Great. So now, and in the process we found out one of the matrix errors. Okay, so now we can totally get rid of this. But I think actually before I go further, I want to make these cubes look more distinctive, right? Currently they're just, you can't even tell where the lines are. So now I want to add in some like borders to the cubes so you can actually like determine where they are. Let's actually just save what we've done so far. Git add then. Yeah, change like rewrote render cube to use like less points and more rotations. Okay, and then I feel like this render cube function is actually like a similar size than it was before, but it's now more, it's conceptually, hopefully it's clearer to me what's happening anyway. Okay, so if we want to add in if we want to add a border to each of these things, I think we can just add in this border by drawing like two triangles, like drawing a trapezoid, and then just rotating the trapezoid around to the appropriate places. And okay, we'll have to do like 24 rotations. It's kind of nasty. Alternatively, we can actually simplify a lot of this by, like, the only thing that's really happening in here is the matrices that are changing. So we can actually create a list of these matrices and then kind of fill up this entire thing by iterating over the matrices. Doing this would then enable us to just specify what one face of this looks like, and all the other faces would follow suit. So let's just do that now. So we can just say matrix list. We want this to be a series of 6 mat33 f32s, and the very first one of these should be the where's this one filling? Should be the identity, and then we want to do the rest. So let's see. This one 180. 270, then rot y90, then rot y270. Okay, and now we've got those. We should be able to simplify all of this. So now I can just say for I ranging from 0 to 6, we want to specify that the cube triangle 2 times I plus 0 is equal to the matrix triangle multiply the matrix list matrix multiplied by triangle A, and then triangle B will go in the ith place here. Okay. Let's just check this compiles. Cube triangles, plural. Okay, great. Still looks the same, but now with way less code. And now, now we can actually start specifying the faces of these somewhat simply. And so now, actually, before we do this, I kind of want to just figure out if there's some way of casting these. Like there should be. I kind of want to simplify all of this as well. This is bothering me. Okay. Let's make these cubes look better. Then once we've done that, we'll then simplify all of this stuff. Then after that, we'll finally start rotating them. But like the linear algebra being simpler, we'll make the rotation simpler as well. So, and the movement and everything. So, okay, we'll continue doing the render grid stuff. The render cube stuff. So, this is what we're doing. Okay, so now we want to have like the edges, and so we'll similarly make a list of like edge triangles, and then we'll draw all of them. So there's gonna be so many edge triangles, but it's okay. So we want to say call this like face triangles, and then we want edge triangles. And so let's draw like a really crude diagram to just help us reason with this kind of. So currently the face triangles look like this. We're going to adjust these. We're going to define some extra points here. And then the face triangles will go here. So I guess this is now if it's this one and that, then it should be like A and B. And then I want to draw these edge triangles here, like a C and then a D. And then we'll rotate these ones around to the other points on the edges, and then rotate all of those around. So there's going to be 24 rotations, but we'll get there. In order to do that though, these need to be adjusted a bit. So in fact, for these ones here, we want to minus from them. We want to like move them inwards. So I could just say something like edge epsilon we'll make this like 0.1 to begin with. And then if this is a 1, we actually want this one to be 1 minus edge epsilon is too big. Let's just call this like EPS epsilon. Yeah, so we want this one to be -1 plus epsilon, -1 plus epsilon. This one is plus epsilon, this one is minus epsilon. This one is, yeah, plus epsilon, oh, come on. This one minus plus, and minus. Okay. Now we've got those, we can define triangles C and triangle C and D. We do want some, we do still want like the original, some of these original points though. We'd actually call this like face 0, 0, face, face, face. And then I might just say like edge 0, 0. And then edge 1, 0. And then, let's see, we're going to have to change the C's in here to the F's. Yep, 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 no, yep, yep, yep. Okay, so what are the coordinates of these edges going to be? The final coordinates will be 1. And then before this, we'll end up with, it should be -1, -1, 1. And this one will be +1, -1, 1. Okay, now we can define these. So triangle C is going to be E0, 0, F0, 0, and E0, E1, 0. And we'll make this black. Well, let's just make it edge color. I'm going to say up here edge color is black to begin with. And for the triangle D, we want a P1 to be E0, 0 as well. But no, that's not right. We want 0.1 to now be face 0, 0. Then 0.2 to be edge 0, edge 1, 0. And then 0.3 to equal face 1, 0. Okay. Okay, so now we have that. We now want to make an array for the edge triangles and move them around. What's an efficient way of doing this? I don't want to manually specify 24 rotations. This is ridiculous, right? But we can just instead specify like 4 rotations to get these triangles drawing on the top of the cube, and then basically apply this same matrix list to get all of the other triangles going. Or how would we set that up? If we just had 2 loops, I reckon we would get them. So let's just write, let's do like the top face edges, and we'll make this to be a constant array of the 8 triangles now. And we'll rotate these in a simple way. So now I want to say for I in 0 going to this, we're going to rotate stuff. To do that, we need another matrix list. So let's call this like matrix face rot matrix or matrices. What am I doing? Matrix list face rot matrices, and then we simply want to have like constant edge rot. Mats is like way easier than matrices. Why did I not change that? Face rot mats. This is now going to be a series of 4 matrices. Mat 33 F32s. And likewise, we're going to want the F32 identity. Let's just really just make a matrix called identity F32. Where's this ID matrix? Const ID. Const. Thank you, zigcomp time. ID F32 is equal to nat 33i82 ID. Okay, now we don't have to write that again, thank goodness. F32, then now we're rotating along the, here, let's just think. The top is this like, the top really means the Z here, and so we're now rotating along the Z axis. And so now we just want to say, like why, something about all of this matrix conversion needs to be cleaned up. I'm not happy with this. But anyway, it's okay. Let's just find peace in the world. Okay. We're just doing a rotation by 90 degrees along the z-axis. That's an F32. Rotate by 80 degrees. Rotate by 270 degrees. Oops. This is meant to be this stuff. And now, honestly, it may just be easier to we can just combine all of these into one, right? Like I don't know. Let's just get rid of these. And why not just add it in even though we just defined it? Come on. Okay. Similarly, get rid of all of these and just say mat33ia2 and this okay. Now I've got all of those. We just want to multiply the triangle C and D appropriately. So we want to say, do we even have like a top face triangles? No, that's not. Top face edges 2 times I plus 0 is equal to edge rot matrix I mat try multiply this thing and triangle C. Likewise, we want to do the same thing with triangle D. And then stuff is there. Okay. Before we start rotating these things around, I want to plot them and just make sure they're behaving. So now we want to say draw edge triangles for edge was it top face triangle? Yeah. What did we call these? Top face edges. Top face edges is vague. Top face. Let's sort out the names. If we say top face edge triangles, this is unambiguous. And then Q triangles, we will incorporate this stuff into this. But for the moment, we just want to plot these top face edge triangles. So top face edge triangles. Draw triangle. Okay, let's try compiling this. 374. Yep, okay. And then 7. I should start making a counter for the number of times I forget to do this. This should be an equal sign. 377, Rod said 180, unknown. Really? Oh. If we did like rot x 90, then 180, 270. Oops, okay. 383. Cannot assign to constant. Yeah, because this is... Okay. Okay, everything's kind of wobbly, but not for the right reason, maybe. Yeah, these edges look like they're in some weird position. Okay. Let's get the math calculated. Let's get the calculations on these correct again. So actually, first off, let's make sure that we're still drawing cubes, but now we're just drawing them in such a way that the faces are smaller. So let's just disable this part for a second. Yeah, this looks off and not in a good way. Okay, so I think our redoing, maybe these are off. I think these EPS things are off. How? This one here is meant to be, so the rule should just be a plus when it's a minus and a minus when it's a plus. Okay, fine, 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 fine. No, that's meant to be a minus. Fine, it's meant to be a minus as well. It's meant to be a minus, okay. Okay, better. There's now these gaps appearing, but this is what we expect. Well, I think this is what we expect. In any case, this looks good enough to continue. Like, let's see, if we're shrinking all of these faces slightly, then we would expect to see gaps wherever the edges are. But in this case here, for some of this edge gap, there's a face behind it, so we don't see it. But then in this stage here, we do see that. Okay, this looks good. This looks fine. So now let's check that this part is working as intended. Okay, let's change the edge color from black to yeah, something that's actually visible. So what are some of the other colors we had? Let's make this like gray blue. Okay, okay, not where I expected the edge, but this is because like it it, it clearly is a correct frame. It's just the wrong size. So we need to scale this down. So yeah, so after rotating these things, we now need to like add the top face edge triangles into the actual triangles of the cube, and then once we package them in them, they'll get rotated into like the correct place. Not that it matters because they're the same everywhere, but then they'll in that process they'll get shrunk and then they'll get pushed to the right place. So we now want to add them to these cube triangles. And so now we want to add in well, let's think about it. I think we can just define like all of this is comp time known. All of this is certainly comp time known. I think we can just define a comp time variable that just has all of this stuff. So we can just say constant top face triangles, and we want this to be the top face edge triangles together with the collection of triangles that is triangle A and then triangle B. And so now we just want to have in here, what would it be? The 6 times that should be 10. We'll just write out the numbers so they're clear. 6 times the 8 plus the 2. And then we want to put these inside another loop. So now we want to say for all of these indices, and then for the triangles, for the top face triangles, oh, hang on, we have to be careful with these indices. Why don't we just say here constant top face triangle n is equal to this top face edge triangle, the top face triangles, and then just the length of it. And then here we want this to be 6 times top face, this thing here. Now inside of this, for each of these triangles, we want to say cube triangles, this is where we need to T top face triangle number times I plus the jth of this is now going to be matrix try multiply the face rot matrices I, then the new triangle. Okay, I think this should be the right loop, but we'll see. Okay, compiler. 696. Oh yeah. the type is triangle, not triangles. Okay. Almost kind of working, I guess. But this I'm not sure why this extra one is getting. Oh, I know why it's getting drawn, because we're kind of duplicating it. We should just eliminate that now. Great. This looks like it's working to me. Okay, let's adjust the colors now, as well as the epsilon. So what's it, EPS? So to me, this looks like an okay thickness, but maybe we could halve it. And then in terms of the color, gray, blue. We could make this more interesting. Why don't we make it a yellow instead? Okay. Okay, it's jagged because we're not doing anti-aliasing, but whatever. It's I'm happy with this. Okay. Okay, let's then save all of what we've done so far then. So we want to do I kind of want to like have this up. It helps looking at it. Cube. Did I not rename it to cube something? Rolling cube demo. Okay. Git status. How much did we? We certainly rewrote some stuff. So now I want to say added outlines to cubes. Simplified render cube. Okay. Off that goes to GitHub. Then I guess we can actually kind of leave like that. Okay, we can get rid of this now. No need to save it since it's working. Okay, now we can actually, we should clean up the linear algebra. Okay, some very long time ago we did some tests where I just wanted to see how the vector multiplication worked, and so oh yeah, how did this one work? Let's remake this again. Debug vec1 times vec2. Why am I printing this? We can do something better. Vec1, vec2, vec3. Capture 1, capture 2, capture 1, capture 2, capture 3. Vec1, vec2, vec test 1. Vec1 times vec2. No need for that. Yeah, and let's just did I not save it? Okay, the point is not to look at the render. The point is to, here it is. Okay, so we had 1, 2, 3, and 0, 4, 1. We get 0, 8, 3. Okay, so it looks like it's multiplying these component-wise. Yeah, okay. Just to make sure, the easiest way to do this, right, is to have like one of them be the identity. 0, 4, 1, and in response. Okay. So then, given this, we can simplify a lot of calculations. Also in terms of the definition of these, I think it's more sensible to think of this as an array of 3 vectors, or just an array of vectors. So now if we say this is 3ia, and then likewise we make this 3f32. We'll need to simplify some stuff, but it will be easier to read, presumably. So I think this stuff should still be fine, hopefully. Where is our first compile error? Oh, it just naturally worked. What? Okay. Unexpected, but I'm not going to complain. So then let's start simplifying some of this. So for this one here, when we're just doing this matrix multiplication, we no longer need to sum over, okay, we do need to sum over those k's, but for this one, we should be able to simplify this. Right, if we're just multiplying the matrix by a vector, and this vec3 is honestly a vector, right, vec3, which it is, then we can just do that operation we did above. So now we just say this entire thing can be replaced with matrix I times the vector. So matrix I times the vector. Then for the matrix scalar multiplication, this is really readable, it's obvious what's happening. But we could also simplify this too. We could say const the scalar vector is equal to a vec3 that's equal to the scalar and the scalar, and then this is just going to be return I is just equal to the matrix I times that. Let's compile this. They're not saving. 131. Wait, what? Oh, right, because we need to... Okay. I was thinking this is the dot product, which it's not, of course. So we just need to like sum this up. Can I do like sum? Is that a compiler intrinsic? No. Surely there is some compiler intrinsic for summing up a vector. I want to use the LLM. How do I sum up a vector in Z? Like, surely there's some compiler intrinsic for this. Oh, okay. What's this vector call? I think this is, maybe this is what is vector call? Okay, yeah, okay, so it would be in here. If there is like an compile intrinsic, okay. The splat at least is something, okay, convert scalars to vectors, so we can simplify that part here. So here we want to say what splat the scalar, and then, presumably. If I specify the type. And then, this is getting too complicated. I think we might have to just go back to the dumb way, which is okay, I guess. So we'll just do why. This is even too complicated. It's simply scalar times the sum, and oh no, what am I doing? No, this is, I'm multiplying an entire matrix by a scalar, and so we should be able to do this with the splat version. It's just that yeah, why was this an issue? Like, I'm confused. Like, does this not return a vector, and then we're just saying that scales every entry in this vector by the scalar, and then we're just saying, so because I haven't defined what the red is. It's more like it's like that. Where did this sum appear? Oh, I started editing a different one. Oops. Okay. We wanted to edit that other one as well. So if it's just a matrix vector multiplication, then I guess we can just say dot is equal to matrix I times the vector, and then we're just saying the return I is equal to dot 0 plus dot 1 plus dot 2. Okay, stuff is still being drawn. It's working. I guess maybe this simplifies it a bit. I don't know. I don't know if this is more readable than what was there before. Anyway, now what shall we do? So yeah, surely this conversion thing can happen. We don't have to literally convert the type of every single entry, given there's built-in vectors. Okay, actually maybe using reduce isn't that bad, if we can like use an add. So, okay, let me do that. So reduce, add, comma, vector. So when I did this thing, I can instead maybe do reduce dot add, and then dot. Okay. And then, oh, this is, yeah, okay, this is, like, the syntax isn't actually that bad now I think about it. This, maybe I still think it would be easier to have this as a compiler intrinsic called like at sum, and just have like at max and at min work for vectors, but I guess it's clear from that what's happening, so it's okay for now. But what is it? We want to like this has to be tidied. So how? We just want to cast vectors, convert vectors. How do we do that? The LLM might have to help us. How do I convert a vector of in zig to a vector of float? And look, at least this isn't C++ where vector is not fixed. It's so absurd. Okay. This is what I did. There should be another way of doing it. Oh, there's like, what to select? What does this do? Selects values element y from A to V based on pred. So what? I'm not understanding this. Okay, if pred is true, the corresponding element will be I1 and otherwise B1. Okay. Uh, in, okay. So you get given. Oh, I see. Okay, so it's just like you have a sequence of ones and zeros, and then you want to use those to like combine two vectors. Okay, curious. Never thought that would be needed, but okay. So can like float from int actually work on vectors? Like it says any type. Like what if we just had for this return I is equal to at float from int matrix I. Is this okay? No, it really doesn't like it. This is annoying. I'm sure I'm not the first person to want this. This isn't helpful. I hope it will eventually work. Oh, it looks like this is when was the compiler 1.11 released? Okay, this is kind of close to when it did. Oh, but it says it's closed, so is it working the current compiler? Yeah, A is just this vector converted. Okay. Like I think I should have a version of the current compiler on here. Or at least something that's about correct. Okay. Let's just make a test. Push the temp vec conversion test. Running max. And then yeah, zig current run test.zig. Yeah, okay. Our compiler is just old, but in later versions this will be fine. Okay. Let's just note that. current line fails with version 0.11 of the compiler, but this has been fixed in version 0.12.0 in a dev version of. Okay, we tried to simplify this, but compiler bug. Zig build that has been fixed. So, why does this not work? Okay. We've cleaned this up a bit, at least, I think. Let's check. Git diff. So we like added more lines here, but maybe it's a bit, maybe there's less characters. -4 lines, add 3. Okay, maybe. Noted this. Okay, I'm really not sure this actually did anything, but now it's more vector line. Maybe linear algebra and alg use more vector stuff. Okay, now we should actually get back to making this cube roll. But we've now tidied this stuff up a lot. So now it's actually like the fun part. So let's see. So currently when I rotate the cube, nothing's changing because all of the colors of the cube are the same. Let us modify this a bit. I want to see different colors again. When we go back to our render cube function, let's start adding in the colors again. So currently everything is the same color, but we want to make these vary again. So we'll add back in the cube argument. And then we need to set these. So, we should first set these to be a debug color, and then once we rotate the triangles around, then correctly color them. So this edge color is fine here, but we want to change these ones to debug. There's a better Emacs command for doing this. There we go. Then we now want to iterate through the colors of the cube when we're doing this stuff. So this one here. Rotate triangles in the top face to other positions. Set cube colors to. So how's this working? Yeah, for each of these top, hang on. This is the combined ones. So we've got the edge triangles here, then we've got the actual face triangles. And then we're saying, this was, I think it was right to combine them. Just we just need to be a bit careful now. So now if like J is it's like if J is 0, no, if J is in the last two, that's when we want to set stuff. Let's actually just rearrange the order of this so it's easier. So we do this first, and then we'll add in the top, base, edge triangles. And now once we've done, when we've iterated over all of those and rotated them appropriately, we just want to set the colors of the first two. So now we want to say cube, let's just say like set colors, cube triangles TFN TFTN times I plus 0 is color 1, and then likewise this plus 1 will be, this will be the same color, and here we want to do what? We want to say like cube dot cube I. I think that's what we want. Under the assumption that did we delete the definition of a cube? No, it's still here. Where are we? Oh, why didn't I save the cursor position? Yeah, that should be fine. Okay, and now when we actually call render cube, we need to pass in the appropriate cube colors. So now we want this to be the red cube again. Make this the green cube, blue cube. And then, did we have a... Do we still have this cube 1? Yeah, we do. So if we go to main, main function please, fn main, okay. Where's this like render cube? Okay, it's in here. We want this to be cube 1 again. Okay. So yeah, let's attempt to compile it again. 401. Expected type triangle right, because we're setting the color of these triangles. Okay, good. So yeah, things are rotating. How was it? Let's see. It's rotating right, rotating left, rotating up, rotating down. Yep, that down. Okay. Let's change the outline color again. We used yellow 2 last time, but now is magenta too much of a color? It is a debug color. What if we just made these cube outlines be white instead? We'll just make this like super energy for all the pixels turned on. Okay, yeah, these are easy to see. Okay, so we want to now start animating this stuff. So I think the first thing to do is to move the physical position of the cube around to the correct places. So let's add in the stuff required for this. I'm kind of hungry. I don't want to get lunch, but yeah, this is moving. So yeah, let's just like physically move the cube around the correct positions. So we go to globals. Let's make one that is defines the cube position. Yeah, so we haven't done any yet. So let's do cube position. We'll make this, it's just a vector. There's actually no need for it to be a float, since really this should be integers. And I just don't want to add in floats and then have like weird floating point errors and then have everything slightly off. I would prefer it to be integers and then we just convert to float when we need to use it in position calculations. And also yeah. Okay, we'll need to define a new type then. To just have like a vec3 of integers. So let's say like vec3 int. And like int isn't a default type in Zig, but this should be okay. And then, alright, make this vec3 int that is currently undefined. Okay. Or really, this should actually be this should be 0. We should make this equal to 0, 0, 0. 0, 0, 0 is where all of this stuff is. Let's instead do like 3, 3. Then time to animate this. So if you key down, here's all of this stuff. When keys are pressed, rotate the cube and update its position. So now we want to say, let's just do like the left key first. So pressing the left key is rotating stuff along the x-axis. And so we want to move it 1 unit to the left, which is then actually 1 unit upwards in the z direction. So now we want to say cube position plus equals vec3 int 0, 0, 1. And we'll have to repeat this for later ones, but let's just get this working and then the rest will just be like copy paste. Now when we actually render the cube, we want to convert the position from from this vec of integers to this vec of floats. Annoyingly, since this is version 11 of the Zig compiler, the float function won't work, so we need to do that manually. So we can say cube position float, which is now a vec3, is equal to, well, it equals a vec3 that's equal to float from int cube pos 0, and then this repeated, but now in the final argument that with a 2 and with a 1, and then here we want this to be cube position float. Float is vague. Let's make it f32. Oh, come on. Why did that happen? Because I'm too used to writing f32. Apparently. f32. Okay. Let's try this. Compile error. Cube pos f32. Yeah, because that's, we're defining it there. Did I call this like cube position instead of cube pos? Cube pos is shorter. What's wrong with that? Let's just replace all instances of cube position with cube pos. Okay. Great, and when I press left it moves. So let's just repeat this, but now with the right key we want to be moving this in the negative direction, and we'll figure it out for these ones too. So when we're pressing down, we want, let's bring this up again. When we press down, we want to move it that way. So in the positive x-axis direction. So make this 1, 0. And then we want this to be 1, 1, 0. Okay, it's moving, which is good. But pressing upwards and down, I got the directions mixed up. So really, press the key up should be moving it down. Okay. Great, the cube now moves. Hoorah. Yeah, and weird effects when it moves in there, but that's alright. Okay. Okay. This is better. And yeah, the rotation, yeah, it really seems to be working now. Okay, good. So now let's change the let's add in some animation so that it 1 rotates smoothly and then 2 like transitions smoothly. So there's no need for this to be all of this like different colors now. We can, let's just make it simple. Make the color simple. We'll make it a yellow cube. So where is it? Cube 1. Let's make everything key yellow. Yellow 2. Okay. because yeah, we observe that it's rotating fine, which means that when we actually start implementing the rotation, it should be fine as well. Okay, git, what did we do? Git, we just made the cube move when buttons are pressed. Made position of cube change when buttons are pressed. Okay. And okay, so let's first implement like an animation for getting for the move, like for the cube smoothly moving from one point to another, and but without the usual crap of like blocking input until the animation is finished. So to do this, let's or what? Oh, we're gonna have to start introducing some timing stuff. So we'll basically make each of these, when each of these buttons is pressed, we'll figure out the end time for an animation. We'll then figure out what proportion of time has elapsed since, well, what fraction of time there is between the length of the animation and the end time. Then that will give us some rational number between 0 and 1, and we'll just use that to like key the animation. Like we'll have an offset, and the cube's position will just be the actual position plus the animation offset at any given time. And then when the button, when the cube is moved left or up or down, the animation direction is immediately set, the animation end time is immediately set, and then stuff should work out. So again, let's just implement this correctly in one direction, and then we'll copy it for the others. So we need to get like get a timer working first. So let's get timer stuff working. But also too, we'll set like an animation time. You can say like constant animation, or like movement. Animation time. Animation time will make this like 1 second to start off with. It is always fun though, just to like actually like move, press things on a keyboard and see stuff moving around. This is satisfying. Okay. Well, I mean, satisfying when you've actually like coded the functionality yourself. When you've like literally drawn all of the triangles and the edges. Okay. So yeah, time stuff. Let's do this. So we use time in one of our previous projects. Let's just find where. We did it as a test in the butterfly quiz. So for the time, measure loading time 266. Butterfly quiz main 266. Zoom in Emacs, thank you. So how do we do it? We did like stopwatch defined where. Okay. We're adding a try now, which means an error can happen. Okay, let's copy that. Set up a timer for the animations. And then, well, when did we use the stopwatch and how did we use it? So we then said, read this, read this thing, and then format it as something. This is in nanoseconds, which we will want to convert, but from memory, like, it was confusing, like looking at the conversion functions. But we'll jump back in again. This was our first project in C when we didn't even know most of the language, so we'll try again. So now if we go, like every frame, let's just read out the time and print it. So we'll just do that here. So we can do constant current stopwatch, and it is nano. And then we'll print this current stopwatch. Let's just see if numbers happen. Yeah, use of undeclared identifier stopwatch. We want to make the stopwatch a global. So what even is the type of it? Vary stopwatch is it like standard.time.timer? I guess it would be. And then we just want to do that. Okay. Start the timer used in animations. Expected type void found error timer unsupported. Maybe we need to look into the source code and figure out the best way of doing this. But I'm confused. Like, why can't I simply? Why would this not work? Expected type void found error. Oh, is it? I think it's because of the main here. I meant to say, like, yeah, right. In this previous one, we had to add in this like any error. Any What? Oh, it's not capitalized. Okay, okay. And yeah, the seconds is going up. As expected, so. Okay, so now we want to like format this so that, maybe we don't, maybe we can actually just keep this in. I just want this number to be in seconds. I just want it to be, oh, what do we actually need it for? Like, we're gonna need it when we're calculating like a ratio of the time that's passed to the current time. And so yeah, let's look into the Zig stuff for time conversion. So go to Zig standard library, time presumably, maybe even not time yet. If I do like nanoseconds, or one of the functions we call it, big milliseconds from nanoseconds. This looks like conversion stuff. Okay, so it's just in time.z. I think we can also leave this butterfly case now. Zig lib standard time.z. I do like milliseconds. Timestamp. What's just set a calendar timestamp in seconds. What is this nano timestamp doing? Oh, maybe this is, no, this isn't, this is just going to save some number, but it's not. It looks like this is the standard way to do a conversion. Yeah, I see it. Divide. So in our case, we're going to take a difference, which will give nanoseconds, and then we'll divide that difference by the nanoseconds per second. Surely there's ns per second, right? Ns per second. Yeah. And then it's like nanoseconds divided by nanoseconds per second is flipping that around, so we will get the seconds, and then we should be fine. Okay. So then let's go back into this and add in these ideas. So I almost think there's actually not a need for a timer anymore. Oh no, there kind of is. Well, the thing is that we could do all of this stuff just in terms of these timestamps. But maybe the timer is more helpful. But if everything is happening just in terms of these timestamps, maybe it's good to see what the methods of this timer function is. Is there an actual file called timer in here? Back to here. Timer? No. We go to time. Two seven seven. Yeah, okay, this is what we should be doing since it's like monotonic and high performance. So then we basically want to whenever a key is pressed, I think we want to what's the idea? So the idea is press a button. You press a button, do something with the timer, and then when you actually do the frame calculation, you figure out what fraction of time has passed since you last pressed the key in terms of the maximum number of seconds for an animation. So in such a case, we just want to lap the timer whenever it's pressed and then read the value of it in any given frame. Okay, so let's update it. Let's update the buttons with this then. Main.jig. So we start this thing and say we do like key down. Then here we want to do let's stopwatch dot lap. I think that was it. Adding these to all of these seems a bit. Anyway. What? Oh, okay. So we'll say like to cast what the value is. And then we want to read it. Yeah, so now whenever a button is pressed, it's reset to 0 again, which is good. Yeah, it's like 6 milliseconds. Good. Okay, and then we now want to like move this animation time to the very top. We do like animation, and here we have this like minute animation time, which is now like seconds times nanoseconds, or yeah, what is it? It's like seconds per nanoseconds per second, right? Yeah. And where is this? Where's this defined? Nanoseconds per second. And time.z. So in main, I want to say standard dot time dot, I guess that's fine, nanoseconds per second. And then we actually want to do the proportion calculation stuff now. So let's go back to main, and now instead of just printing out doing this thing, we just want to do the proportion. So we want to say like calculate the time that has elapsed. So elapsed time nano is equal to, well, literally stopwatch dot read, and then we want to do the proportion stuff. So now we want to clamp this at can I say like clamp? Just a compiler intrinsic. I don't want to do this with an if-else statement. Like there should be a intrinsic for this. In math.zig, okay. Value lower upper, okay. So we just say, yeah, actually, so we actually want to say the elapsed time, well, that's fine, we can say elapsed time planned. Well, I kind of want this elapsed time clamp to be in seconds. But we should. I think it's easier just to have all of the logic written out and then tidy it up if necessary. So now this is just the elapsed time nano times standard.math standard.time dot. We're dividing this by standard.time nanoseconds per second, and then now I want to say clamp time is equal to standard.math.clamp, and what was it? The thing lower upper. So now it's elapsed time in seconds. We can actually avoid this, like, this is just in seconds, since we've converted it anyway now. Animation time. Oh no, 0 animation time. Okay. And now let's just print out this this clamp time. Maybe this is debug. Okay, 230. Oh, why are we not using that? Okay. Okay, it is going from 0 to 1, but I want to see like I want to see the decimal points. So I guess we want to just format this as a float now. Oh, but it's not going to. Oh, hang on. Yeah, it's. I think this is just converting it to an integer. Which we don't want. This is why, like, in the time code, there was, like, division intrinsics and stuff. Okay. Yeah, okay. So we're going to have to do... We want to do this kind of stuff. I just want to float. I just want a float. The correct thing to do is to do times not in floats. Like, I understand why this was done. When you're making a game, you just want the float though. Alright, so what should we do? So we want to do... Maybe the easiest way is actually just convert the overall nanoseconds into a float, convert the animation time into a float, and just do the division then. I feel like that would kind of be the most accurate anyway. Okay. Let's just do this. Now we want to do animation. Okay, let's convert this back to 1 times, 1 times time, standard.time.nanoseconds per second. And then we want to avoid doing this division. And now to get the ratio, elapsed, we have to do the clamping though. So the clamp time should now be this elapsed time in really just this elapsed time in nano, and then we're clamping this between 0 and the maximum animation time. Now we need to convert this and divide. And so now we want to say fraction, like animation proportion. Yeah, let's say animation fraction is equal to float from int. We're gonna have to do like the division thing. We'll continue. Float from int clamped time divided by float from int this animation time, and let's just print this out. Any fraction. Okay, we want this to now be an F32 should be fine. But I just said this should be an F32. As an F32, please cast this. There needs to be a better way this happens. What? Why are we now getting a format print error? Okay, if I just go away. If I just do this. Okay. Right, we got there in the end. This now says a 1, and when we move the cube, and if we immediately move the cube and end the program, yeah, we get the fraction here. Great. Okay, now we can actually continue with the animation. So let's move this to like at debug. Okay, so now we want to well, actually, we should really be doing this kind of stuff after we've detected the key presses. So let's move this down, and we should tidy this in some sense, but whatever. This is fine for the moment. Let's just get this working, and then yeah, now we need to do the position calculation and all of this. So so I think currently in render we converted the or we did this in render cube? No, surely not. Just in the standard render function? Yeah, we converted the cube position from the integers to the floats. We don't want to be doing that here. We want to be doing that in the section where we are actually determining its position using the animation stuff. And so now we want to say this should be a global. Okay. Emacs, what are you doing? I want to go to the globals, please. Okay. Cube position F32, vec3. And then, yeah, so now we set this here. We should call this in the render. So, yeah, cube position F32. Okay, now we can set it. So now we can say depending on the animation fraction, offset the position of the cube. So in particular, we're going to have to determine an animation direction, which will need to be a global. So this is going to be a variable. Animation direction. Let's make this a like vector of integers, a vector3 of integers. Let's set this when we do the input processing. So for like the key, let's get stuff working for the key left first. So for the key left, we want to set the. I need to look at it in my head. When we press left, we're moving in the Z direction upwards, which means we want this animation direction to be the same thing. So we want to say animation direction is equal to this thing. Okay. That's all it's going to be for the moment. We'll add it in later. We'll add it in for the other ones later. And then now we want to say we're going to be multiplying this fraction. We're going to be multiplying this thing by some fraction though. So actually you want it to be a float. That was silly. I should have thought of that ahead of time. It's okay. So make this just a standard vectory. And yeah, do that there. Now we want to say like the animation offset. We want this to now equal the animation fraction times the animation direction. And then finally we want to apply this to the cube position. Animation offset. Okay. I think there's a sign error somewhere, but we'll fix the sign error. 64. Yeah, make this undefined to start. Make this 0 to start with. Likewise, we'll make this undefined since we should only be converting this from the base. Okay, 242. Okay. Right, because in Zig you can't multiply a vector by a float. So in fact we want to just do the number. What was it? What was it called again? When we go back to vectors. It was that name starting with S that we implemented in the linear algebra stuff earlier. Splat, that's right. So we want to do splat animation function. Okay. Must have a known return type. Can I not infer it from this? If I just say this is meant to be a vec3, is that enough? Come on. Animation fraction vector is a vec3 that's equal to this thing. Okay, finally. Okay, and the cube is moving. We press buttons and it moves. It moves in this direction no matter where we press it, but we will fix that. And it's also moving really slowly. I don't like how slowly it's moving. Okay, let's change this. Animation time from 1 second to maybe 0.3. And then let's just do that. Whoa, what just happened? This is the reality. When you do game design, you want everything to be floats, and general purpose programming languages are like, no, this cannot be a float. This has to be an integer. What's the best way around this? Like, we want to just specify a float that represents the seconds, but everything else will have to be. This is annoying. Maybe it's actually not too bad. We will just have to round some stuff. So perhaps if this is a float, if we convert this to a float, we can then change it as a proportion. But then we'll then want to cast it. We'll then want to round it back. So then we'll want to cast it again. But now there's the issue that there's like a floating point issue now. In that, if this is being represented with 64 bits, and we're just multiplying this by some like crude like 0.3, then hey two step. Thanks as always for chipping in. Okay, the thing that if I do that, I would just worry. I would just be. I guess like okay, with comp time floats, then how many bits does a comp time float actually have? Like, is it like as many as needed? Where's the list of all of the types again? Yeah, like how many bits is this? Is it going to be enough? I can try. I can give that a go. I'm just worried about like inserting some weird like timing inconsistency because of stuff getting rounded. Okay, so now this is a comp time float. Is this thing gonna be like of the correct precision? That's what I'm worried about. But okay, let's keep it like that then. Then we need to update this. So now when we're clamping this, we need to cast this, and so we need to cast it. If we just take the floor of it, that should be fine. Or do we want to do ceiling instead? It will. I guess if we're clamping it, it's before the hang on. Or what's happening? So we're doing. This is the thing, like stuff's getting cast everywhere, and there's like a mess of casts. I want like there really should be an easy way of doing this than just like converting everything to floats, doing calculations in floats, and then like converting them back, and then too much is happening. Um, like what's the best order to do this stuff in? Oh. So maybe we actually do all of the timing stuff kind of like after it's read. So maybe there's a way of getting rid of this animation. Okay, so what after getting the nano time, we then just convert it into seconds? Oh, but no, but then there's like, that was the issue from before, where like when we convert it to seconds, it just spits out a 0 or a 1. Okay, but that was because it's still interpreting as an integer. Okay, so if we instead convert this to a float now, and then divide it by the float version of nanoseconds in a second, that will at least give us, yeah, the decent, okay, let's do this. So let's just say, yeah, elapsed time in seconds, but that is a float. We now want to do as f32 let's just do I want to use 64 instead? I feel like it should be, yeah, we'll do it, we'll keep everything f64s for the moment. Float from int the elapsed time in nano, and then we want to divide this by the standard dot time dot nanoseconds per second. Am I missing a parentheses? Yep. Okay, and then we'll like let's push on with it. The animation time can now just be a float. So now let's get rid of all of this and just replace it with the 0.3. And now when we're clamping this stuff, we want to do the elapsed time in seconds. Then we can, okay, yeah, I think this was the right decision. We can now just get rid of all of this stuff. And so now we have, this fraction is just the clamp time divided by the animation time again. So this divided by animation time. And then, okay, let's bring back our debug message of the fraction. And, okay, that's, hopefully we didn't stuff everything up. Time is no member named nanoseconds per second. Yeah, because it was just a S. Expected, where was this one? Okay, we now need to do like the the F64 conversion stuff. So for this part here, I think it will be fine if we just cast this to, an F32 now. Because now both of these are in seconds, and so yeah, it's, but like this was the one that preserved it. Wait, hang on, wait. Like once we've computed this, we can then just like, we can now just treat this as an F32. Like we want to treat that as an F32 going forwards. So if instead, we do as, is there like a float cast? Can I do a float cast in Zing? Okay, I can. Float cast. We'll keep this as like F64, and then we'll just write out, we'll just make it clear that the elapsed time seconds that we want to use from now on is the 32 version. Float cast elapsed time secs. Okay. Okay, and now we've got that, we can get rid of the rush. We shouldn't get this error anymore, I think. Okay. Okay, that was such a like detour, but okay. It's now, yeah, we're now getting this thing animating when we're moving it, and it's moving at, this is still a bit too slow for my liking at this stage, but okay, let's just adjust it. Okay. Okay. My goodness, that was a trial by fire. Okay. So now let's get the animation moving correctly in the other directions as well. There may be something wrong with the offset though, so before we go any further, let's just get the offset stuff working. We might need to clean it up as well. So I should also add in here float from int doesn't work on vectors in version 0.11 Zig. This has been fixed. Fixed in version 0.12. Okay. So So I think like with this animation time, it's going from 0 to 1. When it's at 1, we want the offset to be 0. So in order for the offset to be 0 here, we actually want to multiply this the animated fraction by its like kind of inverse, but this will mean flipping the animation direction as well. But this should at least get us the consistent Q position. Okay. So So let's, where else did we set? Okay, so actually I want this to be like a -1 here. And to make sure this is working, let's initially put the cube at 1, 1. So cube pos, instead of being 3, 3, let's put it here. And we should also turn off this like debug. Oh, what just happened? Oh, I see. We will be splitting 1 minus that. Okay, great. That's the position we wanted in, and it is animating in the correct way. Okay. Let's turn off this debug. Yeah, it's fine. And then we'll want to put this code somewhere sensible. Yeah, let's adjust the animation directions for these other things. So key down moves it that way, so we want key up to move it in the opposite direction. We'll leave it like that. And then, why are there like so many key downs in each of these? What? Wait, how did I like make some? What is this copy pasta doing? Oh no, it's fine. It's fine. Okay. So yeah, we copy this here, put this here, and put this here. And so we want the up and down to move along the x-axis instead. Okay. Let's get this working. Okay, and now yeah, the cube is now moving in the correct directions. Great. And even better, if I press the down key 3 times in a row quickly, it immediately goes there instead of this crappy thing in the bad games where the animation is locked when you press the animation key again. People should be able to like play this puzzle as fast as they want, and that means you press the key 3 times up and 3 times to the right, and you end up there. Or like you should be able to you should be able to do this with the cube and have it work, which it is. This is good. Okay, we finally got the translation animation working for this. My goodness. Let's just save this. Got translation animations working. Okay. Git commit. Okay, so now we need to, actually this was the one I was using for Git. Oops. This was just meant to be the building one. Okay, so now we actually need to like rotate the cube when we're pressing the buttons. So this will require, in a similar way to the timing thing, actually we can use the same, we'll use the same timing button, this like animation time, whatever it was. What is it? We'll use this same like animation fraction to get this thing rotating correctly. But now we'll need to, how will we do this? we'll have some like theta value, and the theta value will range between 0 radians and pi on 2 radians. And then we'll need to make one of these matrices for both the x rotations and the z rotation. And then I think we'll just be able to use this like 1 minus this 1 minus the value version. So then which is to say, when there's no animation playing, the matrix should get multiplied by the identity matrix. Okay, so let's now do this. So yeah, let's head up here and do we can actually just write a function that generates the specific matrix we want. So function matrix x rot theta will be something which that takes in a value of theta, and we'll make this in F32 and returns a 3x3 matrix of type F32. And we simply want to say return the matrix with entries given by, okay, let's say if it's the x-axis, it's going to have the form, if we're rotating around the x-axis, we're fixing it, so nothing's going to happen to that. But there is going to be changes in these values, and this is now going to be cosine of theta, like t for theta. Cosine of theta, this is now sine of theta, negative sine of theta. Then 0 sine theta and cosine theta. I don't want to have to like insert math dot in front of all of these, so let's just declare what those are. So let's just say, yeah, constant sine is equal to standard dot math dot sine, and presumably this would work. And likewise cosine, and then if we go back to this matrix, we'll need to define one of these for rotation around the z-axis. Matrix z, rotation theta. Okay, and now we just want to do something similar. Return F32. We want to fix the z-axis this time. So now it's cosine of theta, sine of theta, 0. Yeah, so yeah, two-step with regards to your earlier question that I've just seen. Yeah, I did just convert everything to floats in the end. Sine theta, cosine theta. And then we're fixing the z-axis, so 0, 0, and 0, 0, 1. Okay. So now I need to start using these to start rotating stuff. So let's now calculate the appropriate theta value from the animation time. So now we want to say, let's like move this way. Calculate cube animation rotation. So we need to calculate this theta. So the theta now is equal to 1 minus the animation fraction times pi on 2. I don't want to I just want to use pi and have it. I feel like I'm going to have to use pi. Oh, what just happened? I feel like I'm going to have to use pi again. So let's similarly import pi here. Standard dot. Surely it's called standard dot math dot pi. Is it? If I just do pi. Do I say constant pi? Not seeing it. If I search tau, is that going to be in here? Okay. I knew if I searched tau, I would find it. Okay, so here it is. Pob const tau 2 times pi and just in math.z. Okay, let's go to math. Z standard library lib standard library math.zig. Okay, it is just pi. So yeah, math.pi is actually just pi. Yeah, pi divided by 2, or really multiplied by 0.5. Okay, and now we want to we basically just want to multiply the cube position by we're going to have to choose which matrix to multiply this by. Let's just do x rotations for the moment. What's the... Given this animation direction determines a couple of things, I want to make the animation direction an enum that we just switch stuff on. So let's just do constant enum, and it can be a byte. That is the animation direction. So maybe animation. There's animation vector and there's the anima. We're gonna have to rename some things. Animation direction. Well, animation type is better. Yeah. Animation type. Make this an enum, and we can have say up, down, left, and right. Let's apply this to this stuff. So now we want to say the animation direction. Yeah, this stuff here. So I kind of want to. I want to factor this stuff out. And instead we'll say we'll set the animation type. So we'll say animation type is equal to dot down, So let's actually make this like a, did not want to make everything capitalized. And then we'll set a global, which is like we'll set it here. Variable animation type. And we'll just make this have a type that is, we can set this to be one of these to begin with, it doesn't matter. We'll set it to be up to begin with. Okay, so then over here, let's set all of these again. So if we're pressing the left key down, we want this one to be left. If it's the right key, we want this to be right. If it's up, we want it to be up, and then down if it is down. Okay, and then we want to switch on this when we adjust the cube position. So cube pause. Where do we do this? Let's do it. Adjust the translation animation offset depending on given which animation is playing. So now we want to say let's say vary translation offset is currently a it's going to be a vector that's undefined, and then we want to switch on the animation type, and then what's the zig syntax for switches again? Oh yeah, it's like the arrows. So now we want to say, do I need to put the dot in there? Presumably. So dot up means the offset is something. And then we do the down, something left, something, and then, well, actually, there's a way to like return. I think switch statements can return in Zig, so I think I can even do like I think I could even say constant translation offset is equal to this. This would be nice if this syntax works. Yeah, something, 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 something. And then these somethings we've basically determined before. Going down the page. We can now like copy them. So yeah, so for the left key it was negative Z direction. 0, 0, negative 1. I just said that was for left. What am I doing? Here. Therefore, for right, it will be the +1 version of that. And then for up, it was 1. so it should be -1 in this case. Okay, and then let's just like align everything again, but not by that much. That's excessive alignment. Okay. Okay, and now I've got that. Now I've got this translation offset. We want to apply it to the position. So now we want to say cube, and like at this stage, the cube position may as well just be a oh, hang on. I feel like I lost distinguishing between setting the position to like an integer value and turning this translation offset. Oh, it's okay. It's okay. Yeah, the cube position is like the one that's important, that gets set like in a single frame. We can now get rid of these animation directions. Okay, and really this here should be animation direction. Animation direction. Okay. Okay, yeah, thanks to Steph. Yeah, thanks for stopping by and helping as always. Okay. Okay, so now that we've done the translation, the animation direction, we now want to choose like the animation, like rotation direction. So really like, I feel like this should rather be like set the like, yeah, set the animation, set the translation animation direction. And then similarly, set the rotation animation direction. Okay. Similarly, we now say animation. Okay. We're going to do something, but before we do that, let's just make sure we get this behavior after compiling it again. So, uh, okay. 145. Another semicolon error. Okay. Now we're getting into the real stuff. Enum missing name up. Is this fine then? Okay, that was. And then 263 local constant shadows animation direction. Yeah. Do we need to know the animation direction outside of this context? No. This is simply to compute the position. So I think we can actually get rid of this global now. So where do we, what was it, defined on 75? Yeah, let's just get rid of that. Okay, and then yeah, we haven't yet used theta, but so let's just like print it out in a debug. Standard.debug dot print the number. Wrap this as debug. Okay. Okay. The cube is still moving and animating in the appropriate direction. And yeah, this theta is now going from what, like one to, the appropriate version of pi to 0. So that was yeah, working. Yeah, we will continue doing stuff. Yeah, so now we actually need to set the, we should save what we've done so far to Git. So we should say, what did we just do? Git commit began to prepare for rotation animation stuff. Okay. We'll push this again. Okay, and then yeah, so now we need to do this. Now we want to say, or really, I think it should actually be like, set the rotation animation matrix. And so I think all of this stuff happens after we've done the time stuff. We kind of want all of this to happen after the time stuff. We really should start wrapping this up in something nice. Let's get it working, then we'll clean it up. So, really, so let's move this theta to, kind of have to do this before we set the rotation matrix. And so now we can say constant animation matrix is equal to a switch of the animation type, where if it's up, we want to return these linear algebra, like these functions that we just wrote. What was it, like, here it is, mat x rot theta. So now we want to say mat x rot theta, theta, and then we're going to have to adjust these appropriately. So okay, so we're going to have to add some minus signs in here and do other stuff and change the x's to something else. So let's see, if we're pressing up, the cube is rotating counterclockwise. No, it's rotating along the z-axis in the right direction. So we want this to be mat z rotate theta. Therefore, down is also the z-axis, but now with negative theta. Left is going to be rotating the cube kind of that way, which it corresponds to rotating around the x-axis by theta, so then right will be negative theta. Leave that here. Okay. Having done that, we now want to. I feel like this is like a global. Well, this is kind of a global that we can pass in when we render the cube. So maybe we actually just now say. Yeah, let's just make this a global. Animation matrix is that thing, so variable animation matrix is mat30 to f32. So now when we go back to the render, we want to there's this cube rotation, so we should say like final cube rotation is this, and then we want to say current the cube rotation we're going to use will equal the our like animation matrix times the final cube rotation. But the times I really mean here is matrix multiply these two. Okay. That's fine. Yes. Let's try and compile that. 292. Do that. It's cold. I need to shut the window or put something on. Okay. And then we've been streaming for a while now. I need to get lunch. So I think once we get this working, I will call it, and then next time will be like polishing this up and making it look like making the code not just everything in the middle of the main function. Okay, so yeah, 75. Oh yeah, this is undefined initially. Expected type 3 vectors 1a. We found this. What, do I not have a matrix multiply for floats? I guess I don't. Unexpected. Like massively unexpected. Okay. Let's just do mat mul f32, where we have. I can basically just copy this entire function. There's some way of doing this with intrinsics. I mean, we'll figure this out later. Okay, we still want this to be f32. Okay. So now when 366 comes around, okay, it's compiling. Okay, great. And now the cube is rotating. Great. I like to see this, but the rotation direction is incorrect. But that is easily fixed. So we actually want to switch the left and the right angles, and likewise we want to switch the up and the down. But one of the down is incorrect as well. But we will let's fix that. So yeah, pressing left should be rotating it with the opposite theta. Oh, we can also we can get rid of this. What's happening? Get rid of this debug. Okay, it's doing it, but it's kind of like currently it's incorrect because the bottom of the cube is going beneath the x-axis. We will fix that. And then pressing down is not working, and pressing up needs to be flipped. So up is flipped, and then down is Z and not flipped. Okay. Let's get this working again. Great. The cube is now moving. Like it's moments like this which are really satisfying. Like you do all of the math, you do the rendering, you code it all, and then you see this. It's good. Okay. And again, remember there's no there's no crappy like bad rotations that happen. Like when if we press these things really quickly, it just skips to the next animation. I can move this down here and quickly switch between the two, and it's just fine. Stuff is not breaking. This is good. Like this, the game that I'm gonna make, it's gonna be so much fun. It's gonna be so good. It's gonna be so good. Okay. So yeah, now let's first of all just save everything that we're doing, and then git add main commit got rotations almost working. Currently the Z offset is incorrect. Okay, so now there's just one final thing to fix, which is now like the position of the cube mid-translation should actually be going on a parabola. Oh, no. It should be going on the arc of a circle. Let's like zoom in the camera to make it evident what's happening. So, it's like if we do like initial camera position of 10, 10, 10, if we bring it into like 666, and recompile, so it's a closer. Maybe this isn't the best angle to see the floor at the moment. like let's change the camera so that it's we'll move it like 10 along the x-axis, not as high, like 4, and then not really that far apart in the x-axis. Okay. Yeah, the floor is way clearer to see now. Yeah, it's like, so now we need to, so in particular, like, okay, when I press left and right here, one of the closest corners should be fixed. And clearly it's not fixed, it's doing something else. And so we need to move the center of the cube in the shape of a like circle with radius equal to square root of 2 times half the size, half the length. Yeah, and then that itself will have to be like an animation offset. So maybe we do this next time. We've been streaming for a while and like it's almost working. I just want the stream next time to be cleaning it up and posting this. But I really should eat. Okay, the question is, can I do this in 15 minutes? What would we need to do? We would need to in the switch part, where is it? Animation, that's the animation direction. Let's just search the switch state and then here it is. I think this thing here, we need to replace. It's rather this offset, this animation offset. We can actually replace this. We can replace these with an animation offset, and these in a similar way that we like compute the appropriate animation matrix. We want to compute the appropriate offset here. And then we want this offset to, to follow. Oh, I gotta do what a break. I want to eat food. I think we're gonna do this next time. We will do this next time. I feel like to do replace animation direction below with something that computes the correct animation offset. That follows the center of the cube on the arc of a circle. Okay. Let's add this to the to-do. So we have started moving and animating the cube. That's fine. We did somewhat simplify the linear algebra. We're not going to bother with the data structure stuff. It's simply going to be, this final to-do is make the translation animation for the cube go along an arc. Adjust, what was it called? Adjust adjust animation direction. animation direction. Okay, let's make sure this compiles for one final time. The cue's rolling. This is cool. This is cute. It's good. Yeah, it's moving. And you can make it move really fast. This is good. I can like see the. Yeah, this is good. Okay, enough pressing keys. Let's save this. Get rid of it. Git add name. Git commit. Then we could say adjusted to-dos for next time. Okay. Push this to GitHub. And let's actually just check stuff on GitHub. There's nothing more I need to change with GitHub after the scope change of this project. So, yeah, a simple demo in which a cube rolls on a grid controlled by arrow keys. But we need to like change the README. We'll do that next time, and then. Otherwise, this looks okay. How many lines is this currently? Look, it could be shorter, but it's also. But we've done a fair bit already. Like simply adding the edges to the cube was a lot. Okay. Likewise, making the colors, yeah. Enough said. And we are like doing this right, yeah. Okay, so now we can, yeah, I'll say like sayonara, or we can even do like the like raid stream button, I think. Let me try that. See if Loris is still streaming. Where's like the raid button? Surely there's a button here that says raid channel. Oh, is Christoph not doing it? Loris. No. Okay, I may just end it here then. Yeah, thanks everyone for stopping by, and yeah, see you next time. Ciao.